Today we are continuing our series on soil health. Last time we talked about what was soil health, but today we're going to get a bit more involved in what soil health is and how it's measured and the interaction between the different parameters or indicators of soil health. Now, as you know, soil health is made up of soil biology, soil chemistry, and soil physical properties. And together these is what give us our soil health. And there's the interaction between each one of them, how one affects the other. But let's start out first with soil biology. Now, when we think of soil biology, we're thinking about the soil fungi and the bacteria, and then there's the different types of bacteria, gram-positive and negative, and actinomycetes. And by the way, that's what makes soil smell so good. But we also have the fungi and other ones. But we also have the eukaryotes. Those are the multicelled organisms like insects and earthworms, springtails, nematodes. So that's part of soil health too. And they say that if fertile soil took all of these organisms together, they would be equivalent to an African elephant on your acre. And that's for a fertile soil. I've heard other people talk about it's more like a cow or two. So it really depends on where you're at about how much the soil microorganisms are there, and also how everything is being managed. How do we measure soil biology? Well, one of our ways our soil health labs do this is through the PLFA, which is phospholipid fatty acids. And what it is that each one of our soil microorganisms has a very particular fatty acid signal, and from that they're able to determine how much gram-positive bacteria you have, or actinomycetes, or how much mycorrhiza fungi there are versus just the more common fungi. But this is a lot of great information, but it's really not as really beneficial to the producer as some of the other ways that we can look at this. Because what it doesn't do, it doesn't really tell us the activity of those soil microorganisms. And one way we can do this is through respiration. We can get respiration measured, and what this does, it tells us the activity of those soil microorganisms. And it gives us a great way that we can compare maybe how some of our treatments are doing. How is no-till affecting the soil microorganism activity? How is using a cover crop or manures or just other management practices, how those are impacting our soil biology. Now, you may wonder also, well, what does soil biology consume? Well, as you probably do know, it's our biomass from our crops, from our trees, from anything that's living and growing. That's what they consume. And without them, the litter in a forest would be hundreds of feet tall. But because we have the soil microorganisms, they break it down. First, the fungi often are the first ones that start breaking it down from the very large pieces to the smaller pieces that have a lot of lignin in them. They're able to break the lignins down, and they would start degrading down. And then once they get smaller, that's when our soil bacteria and others start working on it. Now, when we think of this as our organic matter, and by the way, organic matter is about 58% carbon. So sometimes you hear soil organic matter, sometimes you hear soil carbon. So there is a difference. About 58% of the soil organic matter is soil carbon. Well, when we look at soil organic matter, we see three different phases. We see the very passive stage, or very stable. This is sometimes called humus. This is what's been around for up to 1,000 years. I know there at Sanborn Field, they did analysis on it and found that the humus in the soil goes all the way back to the original prairies a couple thousand years ago. So this is around for a long time. It's very stable. It doesn't change. But this also is what gives us a lot of our good structure of our soil. The next one is more of an intermediate. This is maybe 15 years old. This is still fairly stable. It doesn't change much, but there is some turnover. But what we really are looking at when we're speaking of soil biology is the active carbon. This is the carbon that's probably that year or the last 2 years. This is what the soil microorganisms are breaking down right now. And this measurement that we can get of this it's generally the higher the better. And here in central Missouri, our active carbon is 400 to 500 parts per million. But if we get more into our sandier soils, it's going to be a little bit lower. So you got to really look at what soils you're at and where you're at. Further down in the south where it's warmer, it's going to be lower because microorganisms are much more active and they will burn it off quicker. Now, some labs will call it, instead of active carbon, permanganate oxidized carbon, POXC. And this is the same thing, but that's how they measure active carbon, is through a potassium permanganate reaction. So that's why they call it POXC. But they are the same. Now, there's another source of food for microorganisms, and that's from the plant itself while it's still growing. As we mentioned last time, about 40% of all the carbon that is fixed in photosynthesis by the plant winds up being transported down to the roots and exudated into the rhizosphere, which is then, those compounds then are consumed by the soil microorganisms. Finding out more and more, plants can regulate what soil microorganisms are in the rhizosphere by the compounds that they release. For example, if a plant needs more sulfur or phosphorus, they may exudate compounds that will stimulate those microorganisms that transform or make more available phosphorus and sulfur. So you can see there is this interaction between the plant and the soil biology and also our soil chemistry that we'll get to in just a little bit. One way that we can improve soil biology is through cover crops. Whether annual cover crops or perennial cover crops, we can also improve by manure applications. Also, but then again, having something growing year-round is extremely important. That's why some of the work we found at Sanborn Field was that when we included wheat in the rotation, our soil biology levels were much higher. And we found the same thing when in more recent studies, when we included cover crops. So having something growing year-round helps feed the soil biology and improving our soil health in the meantime. Now, soil biology, the microorganisms, they have a carbon to nitrogen ratio of 15 to 1. 15 parts carbon, 1 part nitrogen. And that's really important because a lot of our biomass that we need to break down is probably 100 to 1 or 50 to 1 or even 30 to 1. So how does that organism then, how can it function and break it down in that it has to take up nitrogen from the soil? That's why a lot of times you'll see farmers say that, hey, when I used a cereal rye cover crop, it seemed like the grain crop afterwards was nitrogen deficient. And when I applied more nitrogen, I got a response. And part of that reason is soil microorganisms are tying that nitrogen up to break down the biomass from the cereal rye crop. So we have to consider that also. So this also links us the importance then of soil chemistry. How much nitrogen do we have in our soil? As we know, it is released from when it's broken down from the organic matter or when we have a turnover of our soil microorganisms. One of the things that we often noticed is that when we do kill out a perennial crop, or if we even till a perennial crop down that's been there for several years, we'll get a big flush of nitrogen in the soil, and you can tell in the next crop. The unfortunate thing is this is only a 1 or 2 year benefit that you get. After that, the soil is much, much less quality. So we don't want to do that, but that just tells us how much nitrogen is tied up in the soil biology that is continuing to be turned over. Now, also when we think of soil chemistry, we of course think about our calcium and magnesium, potassium and phosphorus, and our sulfur and our micronutrients, and they're incredibly important, and as well as our pH. And when they are adequate for good plant growth, then we get more plant growth, we get more biomass, we get more exudates into the rhizosphere and more biology. So we are tied together that way. We also tie together a little different way. Some of our cations, especially the ones that have a +2 charge like magnesium and calcium, can help bridge the negative charges on the soil particles to help build soil structure. And that's incredibly important for us to get good soil structure that leads to other good soil properties like aeration and water holding capacity. So we got to keep that in mind too. But also the soil organic matter helps build these aggregates, as well as the soil biology itself. The fungi produce glomalin, which helps stick the soil particles together, and also bacteria does a similar response. So as you can see already, that chemistry and biology are tied together, and they are also tied to the soil physical properties, which I think is what all of this comes down to, is improved soil physical properties. Because when we build our aggregation, when we take soil particles and build them together, we get closer to that ideal soil. A 45% mineral that has 25% air, 25% water, and that comes from pore spaces, and 5% organic matter. As we have better biology, better chemistry, we get that formation happening, and we can measure that by water soluble aggregate stability. And we get that as a percent. It really tells us how stable our soil particles are, our aggregates are. Do they break apart really easy? Or are they held together in a resilience to rainfall, for example? So this way, they'll have better aeration. They can hold more air. They can hold more water, and that's very, very important today because our climate scientists are telling us, and we're observing that our rainfall events are getting more intense and further apart. So as a result, we need to have a soil structure that can hold more water to get us through these long drought periods. And a perfect example of that is what we observed in the summer of 2024. There at Sanborn Field, we had side-by-side plots that had been managed the same except for one thing. One had manure applied every year, where the other one didn't, just all the NP and K in lime that it needed. And in June, when we were having a dry spell on a warm June day, we could see that the corn on the right did not show any water stress. The leaves were still fully turgid, not rolled up at all. Whereas the one on the left that had not had manure, its corn leaves were starting to roll up to try to avoid the drought. They're trying to conserve water this way. And one of the big differences in the soil was the one with manure had about 2.5 times higher percent water stable aggregate stability, 29, than the one on the left that only had 12. So as you can see, it makes a big difference about getting the more water into the soil. Now you got to be a little bit careful about aggregate stability because higher clay content will make it go higher. So you really need to compare apples to apples. You only want to compare on your farm or similar soils in your area. So many times what we're seeing in soil health is a great comparison. And often what we like to do is compare to our fence row. We can compare our fields to our fence row because our fence row often hasn't been tilled in decades. It often has a very diverse types of plants in it, which also allows us for greater soil health scores. So by comparing that, we can really see some differences in where our soils rank when we want to compare. So how can you improve your soil health? Well, we talked about cover crops. We talk about length of rotation, not just having 1 or 2 species or crops in our rotation, but let's expand it. Let's go corn, soybeans, and wheat. And maybe and then we'll have cover crops in between our corn and our soybeans. Where we can, in a diversified area, if we can have a perennial forage crop in there, maybe it's red clover that we overseed into our wheat. We have red clover for the next couple of years, and then we can follow that with corn. We have found that that makes a big difference on not only corn yield, but also the soybean yield afterwards. So what we've found is that we'll see this echo effect of a perennial crop for 1 or 2 or even 3 years later. So it makes a big difference on what we're doing. Another factor that we can do is that we can apply manures. If available, applying manure, it provides a source of carbon. It also supplies the nutrients. And this helps our soil biology, our soil chemistry. And as we saw in that Sanborn field example, we got better aggregate stability. Now, there's one more things of physical properties that we may want to think about, and that's bulk density. Now, bulk density, water has a bulk density of 1, our silt loam soils have a bulk density about 1.2. I've seen our sandy loams going to about 1.3.5 to 4. So that's a typical range that we often see. But what we found is that just in a few years of being in a longer rotation or having a perennial crop grown in, we can reduce the bulk density, which is a good thing. We make the soil more open, more fluffy, better able to hold more water and aeration when we have that. But we can get it down to 1.1, which is a 10% difference, which makes a big difference. So there's lots of things that we can do, again, to improve our soil health, and these are adoptions that we can do. Probably the biggest detriment to soil health is tillage, and I know many farmers have gotten away from tillage, but there is a time that we have to. And we always say, if you're going to till with a purpose, because we know that often things happen, ruts from a wet fall or whatever. But as our soils become better, our soil health scores go higher, we'll see that our soils can become more resilient and we don't have some of those issues. Well, this is it for today. We'll continue these and we'll tell you more about our research and what we have found in corn and soybeans and how they differ in their soil health factors. We'll talk to you next time. We want to thank the United Soybean Board for sponsoring this research that made it available for us to bring this video to you.